Okay, now that I've got you questioning the value of statistics at all based on Mark Twain quotes and my complaints about the inaccuracies of all these things, well, we can go on and talk a little bit further about how this stuff actually works. So, as the title says, we're going to talk about hypothesis testing. And ultimately, with hypothesis testing, we need to understand how that hypothesis is actually tested, and how do we do that with the actual statistic. And the rest of the quarter, we're going to start talking about the statistics that we would use to test these hypotheses, but we also have to understand how they're applied before we get into how to interpret the individual stats. So let's move on and talk about our hypotheses specifically. Right? First off, the research hypothesis. When you're going to do a study, or when a study is done, the author is always asking a particular question. In other words, is direct instruction better than whole language, or whatever? Right? So there's a research question in there, and then based on the existing literature, you would formulate a hypothesis. For example, let's stick with the DI stuff. DI will outperform a whole language approach to teaching children to read. So there's a decent research hypothesis. The problem is that for various reasons, we can't test the research hypothesis itself. All we can really test is the null. Right? So the null hypothesis is the nulling. It's not the opposite. A lot of people think that the null hypothesis is the opposite of the research hypothesis. That is not the case. It is the research hypothesis neutralized. In other words, given the absence of any other information, it is no difference between your groups. That is always what the null hypothesis is. So the null hypothesis predicts that there would be no difference or no change. In other words, it predicts that your independent variable will not have an effect. So we can test that null hypothesis specifically. We can say, what's the probability that the IV did have an effect? What's the probability that the IV did not have an effect? But it's always about testing against this null. We're going to say, no, that null did not, it was, there was a difference, which means we can reject the null, and we'll start to talk about the terminology with this here in a moment. So let's look at that research question in general. All research questions, if you're using inferential statistics and large group designs, as this course we're talking about for now in this course, is all of the questions, no matter what the topic is, DI or anything else, it's always this: are our two samples drawn from a different population? Control group, experimental group. That's our samples, right? So is that control group now functionally a different population of people than the experimental group after the independent variable? That's what we're getting at. Right? And we talked about that previously. We looked at those curves and how they separate and all those things, and this is the core question that's being asked. And our statistics will allow us to do that, right? To answer this particular question. Are they from a different population or not? And we can state with a certain degree of probability that they are or they aren't. Right? So let's look and see how this works. I've talked about this a couple of times. I stumbled over it the first time, but here we go. We have systematic variance, right? And we'll get to our inferential statistic here in a second. But systematic variance is the differences between your groups. So think of this, the easiest way to think of this is the mean from one group and minus the mean from another group. So your mean from the experimental group, subtract the mean from the control group. That is your systematic variance. Now, we also know that we have to calculate the variances in there, so this is actually a really big statistic. It's huge, right? Because you have to calculate variances for each group and then subtract those variances from each other and then end up with the means and the standard deviations and blah, 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 and all that stuff. And each statistic that's out there does this a little differently, but they all do the same thing. They take that systematic variance, the difference between your groups, and they divide it by the difference that exists inside of each group. So that's the unsystematic variance. The systematic variance is the variance that is due, the changes that are due to your independent variable. The unsystematic variance are the changes, the differences in the scores that exist within each group that are due to things other than that. So like, for example, individual differences or random differences between your people. We're not all the same. We're close, but we're not all the same. So we are going to get different scores on these things. And as a result, we have to take that into account. And because those individual differences also show up in the differences between the groups, we need to remove them from that overall, from those differences between the groups. So we're going to get that systematic variation, we're going to divide it by unsystematic variation, and we're going to end up with a ratio, right? And that ratio, okay, is a number, right? And that number is the inferential statistic. when we have that statistic, I don't care if it's an ANOVA, a t-test, a regression, or whatever, there's always going to be a number. And when you get that number, that will tell you if there is a difference between your groups. In other words, are your two groups now drawn from different populations? In other words, did the independent variable have the effect that it was supposed to have? And then we'll put this into terms of the null hypothesis here in a minute. When we get that inferential statistic, when we get that number, we ask a simple question. What is the probability of that number occurring? If that number occurs at a probability that is lower than your alpha level, remember your alpha level is the level that you choose for, that's your significance level. So oftentimes in psychology we choose 0.05. So the probability, so a p-value is also an alpha level, and so on and so forth. Anyway, so we're going to say that our alpha level is 0.05. That's the level at which we're going to say stuff is significantly different. And we're going to get our inferential statistic, then we're going to go to a table, and on that table, this is all done automatically now, so this is a bit of an archaic way to describe this, but this is how it's done. You get that inferential statistic, and then you go to a table, and on that table you look up sample size. And you look up what statistic you're using. So if we have an ANOVA, we're going to go to an ANOVA table and we're going to say, all right, what was our sample size? In other words, what was our degrees of freedom? We'll talk about that later. That's just n minus 1 or n minus 2 or n minus whatever, depending on the type of design that you have. All right? So we're going to look that up and we're going to say, given this sample size and given this type of statistical procedure that you used, you're going to find that number on the table, and then you're going to be able to read across the table and say, what is the probability of it occurring? And the answer is whatever, right? So whatever that answer is. Right? So it's going to be, what's the probability of that level or that number occurring using that particular stat? So to say an ANOVA, then it will give you a number. If that number is less than 0.05, and our alpha level was 0.05, then we now say it's significant. In other words, this is less than a 5% chance of occurring randomly. In other words, the differences between our groups are real, with a 5% chance of us being wrong. Right? So that's that alpha level. Right? So you could set your alpha level at 0.01. Then when you look up that number from the green box there, when you look up that number now has to have a probability of occurring that is less than 0.01. You could do like physics and go 0.000002. Right? And so on and so forth. It makes it harder and harder and harder to get significance. In psychology, we typically use a 0.05. And you make adjustments to that 0.05 depending on the type of data that you have and the type of experiment that you're doing and so on and so forth. But 0.05 is a good starting point. So we're always going to ask that question, what's the probability of that statistic occurring? And we look it up. And if that's less than 5%, we're significant. That's all there is to it. Okay. So let's look a little further into statistical significance. First off, we got one-tailed tests, and we also have two-tailed tests. So we'll come back to that two-tailed test in a second. So a one-tailed test, we have an alpha level, right? So our alpha level is 0.05. Now, a one-tailed test simply means you are predicting the direction that your group is going to be, the direction of change between your groups. Is your experimental group going to be better or worse than your control group? You predict that sometimes. If you do predict that, then you have what's called a one-tailed test. A one-tailed test means your 5% occurs on one side of that normal distribution. It's like, oh, okay, well, what normal distribution are you talking about? The normal distribution I'm talking about are the ones that I had in that chart earlier, right? So are on the previous lectures where they're overlapping each other. One of the things that we know about these statistics, say an ANOVA or a t-test, is the number that is generated. Remember that green box from the previous page right here, right? Those numbers, when you plot all the possible numbers that exist, and trust me, there's statisticians that do this, when you plot all those possible numbers that exist, they end up normally distributed. Right? So, and because we know about normal distributions, which are also known as probability distributions, then we can figure out the probability of a particular number occurring. And we've gone through that, and it makes sense, and I'm not going to repeat all the logic there, but remember that those normal distributions are probability distributions. So when we are looking up the probability of a particular number occurring, we're saying that that it has to fall within a particular range in that normal curve. And remember, between -1 and 1 standard deviation, there's 68% of your data. So the fact that your the statistic falling in there has a 68% chance of occurring. But that's bigger than our alpha level, right? Our alpha level is 5%, so we need to get down to that 5% range. With a one-tailed test, we're only worried about 5% on one end of that normal distribution. In other words, just above 2 standard deviations or just below 2 standard deviations from the mean. So either negative or positive. So we've got a little bit of wiggle room in there, and we're going to lump that all on one side. So 5% of the data falling on one end of that scale. And what's the probability that our statistic came from that area? And if the statistic comes from that little area, if the probability of it occurring falls within that little tail out there, then we say it's significant. What I tend to use the most are two-tailed tests. These are exploratory in nature. This is where we're not going to predict a direction of change. We're just going to ask the question, is there change? Now we're going to take our alpha level, okay, our 0.05, which remember was before, and then one-tailed test was on one end of that normal distribution. Now we're going to split it into 2, and it's going to become much smaller. Right? So the statistic now needs to be more extreme, right? Because you have 2.5% of that 5%. So you got 5% p-value of 0.05. That's our alpha level. So our alpha level of 0.05 here, we're going to divide that by 2. So that's 0.025. So we're going to take that 0.025 and put it on one end, and another 0.025 and put it on the other end. So now, in order to be significant, our normal distribution, or our statistic, has to pop up in either one of those two areas. It's a total of 5%, right? But it's got to be more extreme. It's further out that curve. In other words, 2.5% of the 2.5% chance occurring. So it's way on the extreme end. So with the two-tailed test, it's actually more rigorous, it's harder to get significance, and it's more conservative. So I tend to use that. But the real rule of thumb here is that you only use two-tailed tests if you're not predicting a direction of change. And things like DI, there's so much evidence out there that says that it's a superior method for teaching people how to read that you wouldn't really use a two-tailed test. You would use a one-tailed test. But I mean, you could use a two-tailed if you want to. It's harder to get significance, but there's no reason to. You have plenty of data that tells you that you should predict a direction of change. So I kind of hinted at some of this stuff earlier. So let's get into that null hypothesis, and let's get into error and those types of things and how we deal with error and all this stuff. So one of these is really straightforward. The other one's a little bit confusing. So in statistics, remember, we're testing the null. So we can either reject the null or we can fail to reject the null. We can never accept the research hypothesis because we're not actually testing that. We're testing the null. So we have to always put our statistics in terms of the null. So let's look at the chart here. Up top, we've got the null hypothesis is, in reality, remember this is not based on our experiment, this is reality. If the null hypothesis is true and we did not reject the null, in other words, our statistics showed us that it was not a significant difference between the groups. So we failed to reject it. There was no difference between the groups, and in reality, our null hypothesis is true, then we have met our research objective. If our null hypothesis in reality is false, and that there is a difference between the two groups, in other words, the two groups are really from different populations, and we reject the null, we've also achieved our research objective. In other words, we found a difference. Rejecting the null means finding the difference between your groups. So we found the difference between our groups, and in reality there was a difference between our groups, therefore we've achieved our research objective. Type 1 error. Type 1 error is finding something that isn't there. So I'll say that again. Finding something that is not there. It is a false positive. So in reality, if our null hypothesis is true, but we will go ahead and reject it based on our statistics, we made a type 1 error. Interestingly enough, type 1 error is also your alpha level. Your alpha level is set at 0.05. You can choose whatever, but for sake of argument here, our alpha level is set at 0.05. In other words, we're saying we have a 5% chance that we're finding a difference when there really isn't one. A 5% chance that this finding really is random. Okay? So that's our type 1 error. We've dealt with that already. If you want to reduce type 1 error, you just choose a smaller alpha level, 0.01. Physics uses an extremely small alpha level, right? Because they don't want to run into type 1 error. They don't want to find something that isn't there. So, and again, finding something that isn't there is saying that there's a difference between your groups when in reality there is not. And if we put that into example, saying that, oh, DI worked really well, is significantly better than some other method, but maybe it's not. If it's really not in reality, then we just made a type 1 error based on our statistics in our experiment. There's a lot of reasons why you would end up with that, and oftentimes it's just a sampling issue. Okay? Type 2 error is a bit of a bigger bugger, so to speak. It's kind of harder to deal with. This is where the null hypothesis is false, but you failed to reject it. Right? There should be a difference, because in reality it's saying that there is a difference between your groups. But the result of your statistics said no, there is no difference. Right? So that's a type 2 error. Type 2 error is a little harder to calculate, and we'll get to it here in a second. But let's look specifically at it. This is rejecting the null when it is really true. In other words, you're blinded. You're not seeing something that is there. It's a false positive. Not seeing something that is there. Type 2 error is directly related to something called power. Okay? So, in fact, 1 minus beta, beta is type 2 error, 1 minus beta equals power. Okay? So power is the probability of rejecting the null when it really is false. So the probability of you rejecting the null when the null is false. The probability, and another way to state this is that power is the probability of not making a type 2 error. A lot of times in statistics or in experimentation, we run into this situation where we get a difference, or we get no differences between our groups. We have to immediately ask the question, is it a type 2 error? And the only way to know the answer to that is to run what's called a power analysis. Right? And we'll look at that power analysis here in a second. So anytime you see this and you're the one doing the research, you ask this question. Now, interestingly enough, most research that doesn't have a difference between groups is not published. There's a problem with that by itself, but so you don't run into this too much as a consumer of information, but when you are a generator, you do have to run into this, and we do have to worry about it, so that's why we're talking about it now. Why is this not going to the next slide? There we go. All right, so pre-planning. Power is going to ultimately be related to sample size. So when we have if we have a large sample size, we have a bigger probability of being able to detect an effect. In other words, we have more power. So we can do a power analysis in advance. There's software out there that you can get. In fact, one of the best that's available is called G Power, just the letter G and then space power. It's free, and you can analyze this stuff. Right? And you can decide how many people ahead of time before you run your experiment that you would need in order to have a certain level of power. So when you're first designing an experiment, you typically do a power analysis, and this allows you to design a better study. Okay? And specifically, you're going to be addressing issues of sample size. But in order to do a power analysis, you have to estimate what's called the effect size. Right? So in other words, how big of an effect does my independent variable have on people? Is it small? Is it big? Is it medium? You actually have to estimate that. And when you estimate that, if you have a big effect, then you don't need, so if you have a huge effect size, you don't need that many people to have a high power study. In other words, a low chance of making a type 2 error. If you have a weak effect size, like for example that aspirin stuff, aspirin and taking aspirin to prevent heart attacks, that the effect size on that is unbelievably small. Right? But if you run 10, 20, 30,000 people through a study, it will be significant. And that's because you have so many people. But it's an example of using that as an example here to talk about how the power is directly related to effect size and sample size. So as your effect size goes down, as your effect gets smaller, you're going to need a larger sample to detect the effect. As your effect gets bigger, you can use a small sample to detect the effect. Right? But either way, we have to estimate effect size. Well, let's think about effect size at a slightly different level here. This darn thing, this is hilarious. I'm hitting the button and it's not going forward. Let's try it again. There we go. All right. So, in order to estimate this effect size, we need to analyze our data a little bit. And in order to analyze the data, we need to think about a couple of things. So let's assume we're significant, all right? We're going to come back to effect size here in a second, so you'll see how it all relates here in just a moment. Right? So let's assume we are significant, and then we're going to ask that question, does that significance mean anything? And statistical significance simply says that's the difference between the difference between these groups is real, It is something that is due to the independent variable, and that it's not due to chance. But the question is it meaningful? So let's think about this. We got and we got 10,000 students from WSU, we got 10,000 students from Eastern. Let's compare their GPAs. There's a lot of people there, right? So it would be easy to get a significant difference between the groups. So if we had, let's say, a GPA of 3.4 from Eastern and 3.3 from WSU, so that might end up being statistically significant, the average GPAs, right? So that might end up being statistically significant, but is it practical? Probably not. It has no practical significance. A 3.3 to a 3.4, that doesn't mean anything. So practical significance is a measure of meaningfulness. Well, we actually have a way to calculate meaningfulness, and it is effect size. So remember I said we're going to estimate effect size up here. We need it to estimate effect size to do our power analysis, to find out how many people we need in our study, to find out if there's a significant difference and be able to rule out type 2 error, all right, and all that stuff. So we're going to get back to it. Here we go, effect size. So we can calculate effect size. It's called Cohen's D. It really is about the difference between your groups. So all we need to do is take the mean of one group and subtract the mean of the other group, and we've got a simple measure of effect size. We could divide that by the within groups variance. Remember, that's the stuff that random individual differences, right? And that would standardize it, and that's exactly what we do. Then we can put it in terms of our prediction, and this allows us to know, this allows us to know the sample size that would detect an effect if there is one. So if we assume that DI has a low effect, then we would be able to figure out how many people we would need to detect an effect then in each group. And then we would, if we assume DI had a large effect, we could then plug that into the formula here and figure out how many people we would need to detect an effect with that large effect size, right? And then you would need fewer people. So what we typically see in psychology, though, is medium to low effect sizes, so usually not these really big ones. Right? So in terms of prediction, we can use effect size ahead of time to inform us how to build our study, right? Which is all about getting back to that power analysis. Right? But in terms of analysis, it allows you to interpret your effect, right? And it allows us to understand the meaningfulness of the statistic. Right? So it allows us to interpret it. Is that statistic meaningful? It may be significant, but you have to ask that question next. Is it meaningful? And a low effect size may say, yeah, it's significant, but it's not meaningful. Right? So in NS here, so is the non-significant, is that a result of low power? So when you run a study and you get something that no difference between your groups, you can immediately run effect size and see that it's so small that there's no way you would have detected an effect because you didn't have enough people. Right? The other side of this coin is that is the effect shown a result of oversampling? Did you get too many, did you just get an effect because you had 20 million people in your study? So if you had, let's say you had 20 million people in your study, your effect size could be so small and it could still be significant. Well, that's kind of oversampling. You're overdoing it, right? So a rule of thumb that somebody once told me, and it was my professor that taught me this stuff actually years ago, was that it's much cooler and much more, convincing to show me an effect with a small sample size, to show me a significant difference with small sample size, than it is to show me an effect with large sample size. I'll let you chew on that one, and we'll come back later and talk about some other stuff.